Welcome to the video. Today we're talking about every type of dark matter. Watch to the end for chameleon dark matter, mirror matter, dark fluids, and some quantum chromodynamics. Dark matter is a form of matter that does not emit, absorb, or reflect light and does not interact with electromagnetic radiation. Cold dark matter, CDM, is a theoretical form of dark matter that is believed to play a crucial role in the formation of large-scale structures in the universe, such as galaxies and galaxy clusters. The term cold and cold dark matter refers to the fact that the particles are thought to be moving relatively slowly with a low thermal velocity compared to the speed of light. Cold dark matter is a popular candidate because it provides a good match to the observed distribution of galaxies and galaxy clusters. The slower motion of CDM particles allows them to clump together more easily, leading to the formation of dense regions that can collapse under their own gravity to form galaxies and galaxy clusters. These particles are cold, non-interacting, and have negligible masses. Warm dark matter, WDM, is characterized by particles with masses and velocities intermediate between those of cold dark matter, CDM, and hot dark matter, HDM. The speed of WDM particles has an impact on the formation of large-scale structures in the universe, such as galaxies and galaxy clusters. WDM better explains the observed distribution of smaller-scale structures, such as dwarf galaxies and the central cores of larger galaxies. Warm dark matter particles would have velocities high enough to suppress the formation of small-scale structures, leading to a smoother distribution of matter on small scales. Some of the proposed candidates for warm dark matter include sterile neutrinos and gravitinos. Hot dark matter, HDM, particles have high thermal velocities, typically moving at speeds close to the speed of light. The high velocity of hot dark matter particles makes them less effective at forming the dense regions required for the formation of galaxies and galaxy clusters. HDM particles would tend to smooth out any density fluctuations in the early universe, leading to a more uniform distribution of matter. HDM is most likely made up of neutrinos, specifically massive neutrinos, which are elementary particles that interact very weakly with matter. These neutrinos can only account for a small fraction of the total dark matter, and the dominant form of dark matter is likely cold or warm. WIMPs, weakly interacting massive particles, and SIMPs, strongly interacting massive particles, are two categories of dark matter particles. Both types of particles are massive and interact via non-gravitational forces, but they differ in the strength of their interactions. WIMPs have masses typically ranging from a few giga-electronvolts to a few tera-electronvolts and interact weakly with ordinary matter through the weak nuclear force. WIMPs are considered an attractive dark matter candidate because they naturally arise in several extensions of the standard model of particle physics, such as supersymmetry and models with extra dimensions. In the early universe, their abundance could have naturally reached the observed dark matter density through a process called thermal freeze-out. SIMPs interact more strongly with ordinary matter than WIMPs do. Unlike WIMPs, which interact primarily through the weak nuclear force, SIMPs interact through the strong nuclear force or through a new strong force that is specific to dark matter particles. SIMPs would have an impact on small-scale structures. QCD axion dark matter refers to a type of dark matter based on axions. The axion is a light, neutral pseudoscalar boson that arises from the theory of quantum chromodynamics, QCD, which describes the strong force that binds quarks together in protons and neutrons. Axions are predicted to have a very small mass, typically in the range of microelectronvolts to millielectronvolts, and interact very weakly with ordinary matter. This makes them an ideal dark matter candidate, as they could account for the observed dark matter density without clumping too much or interacting strongly with visible matter. Axions can be produced in the early universe through a non-thermal process called the misalignment mechanism, in which axions are created due to the misalignment between the initial axion field and its minimum energy state. This mechanism can naturally generate the observed dark matter density. Chameleon dark matter particles have a unique property. Their mass is not a constant value, but instead depends on their local environment. The term chameleon is used to describe this behavior, as it metaphorically changes its properties according to the surroundings, much like how a chameleon can change its color to blend in with its environment. Chameleon particles are often associated with scalar fields, which are used to explain phenomena such as dark energy or modifications to gravity. In this context, the chameleon mechanism arises when the scalar field couples to ordinary matter, causing the effective mass of the scalar field particles to vary depending on the local matter density. In regions of high density, like the Earth or other celestial bodies, chameleon particles would have a high mass, leading to a short-range force. In regions of low density, like intergalactic space, they would have a low mass, leading to a long-range force. This could explain why dark matter has not been detected in laboratory experiments, as its properties would change depending on the experiment's conditions. Self-interacting dark matter, SIDM, is a model where the particles can interact with each other through some unknown force, in addition to the gravitational interaction that all dark matter particles experience. In the SIDM model, dark matter particles can interact with each other, leading to the exchange of momentum and energy. These self-interactions can influence the distribution and dynamics of dark matter in galaxies and galaxy clusters. For instance, dark matter self-interactions could lead to the dispersion of dark matter particles in the central regions of galaxies, creating cores instead of cusps. They could also alter the formation and evolution of dwarf galaxies. Fuzzy dark matter, FDM, proposes that dark matter is composed of extremely light particles, typically in the range of electron volts, which exhibit wave-like behavior on the scale of galaxies. These particles are often referred to as fuzzy because their de Broglie wavelength, which characterizes their wave-like nature, is on the order of the size of galaxies, resulting in a diffuse, non-localized distribution of dark matter. In the FDM model, the extremely light dark matter particles are described by a wave function that obeys the Schrödinger-Poisson equation, which couples the quantum mechanical behavior of the particles with the gravitational potential. The wave-like nature of FDM particles leads to a phenomenon called quantum pressure that counteracts gravitational collapse, preventing the formation of dense cusps in the centers of galaxies and leading to a smoother distribution of dark matter. Composite dark matter suggests dark matter particles are composed of smaller, more fundamental particles called preons. In this model, dark matter particles are bound states of preons, which interact through a new strong force, similar to how protons and neutrons are made up of quarks bound together by the strong nuclear force. In the composite dark matter model, the preons and their interactions could give rise to different properties of dark matter particles, such as their masses, lifetimes, and interaction cross-sections with other particles. Decaying dark matter proposes that dark matter particles are unstable and can decay into other particles over time. In this model, the dark matter particles have a finite lifetime, which could range from fractions of a second to the age of the universe, depending on the specific properties of the particles and their interactions. The motivation behind the decaying dark matter model comes from observations of unexplained excesses in cosmic ray spectra and gamma ray emission from certain regions of the sky. Decaying dark matter products could be relativistic particles, such as neutrinos or photons. Hidden charge dark matter suggests that dark matter particles possess a small electric charge that is hidden or minimally coupled to ordinary matter. In the hidden charge dark matter model, the charged dark matter particles would interact with ordinary matter through the electromagnetic force at a much weaker level than typical charged particles like electrons and protons. The presence of these particles could lead to subtle effects in various astrophysical and cosmological observations, such as small-scale perturbations in the cosmic microwave background radiation or the distribution of dark matter in galaxies and galaxy clusters. Unparticles dark matter describes a type of matter that does not have a definite mass or energy. In the unparticle dark matter model, dark matter particles are unparticles that interact with ordinary matter through a new force carrier. The unparticles could have a range of possible masses and interaction strengths, leading to a wide variety of possible signatures in astrophysical and cosmological observations. Relax ion dark matter is a model based on the relax ion, a particle that is coupled to the Higgs field, which gives particles their mass. In this model, dark matter particles are relax ions, and their mass is determined by the Higgs field. In this scenario, the relax ion particles become massive and can be stable if they do not have any other decay channels available. These massive, stable relax ions can then serve as dark matter candidates. This could explain why dark matter is so much heavier than other known particles. Symmetric dark matter particles have an exact mirror image of themselves, called a dark partner. The dark partners would interact with each other through a new force carrier, which is often referred to as a dark force or dark photon. Dark matter particles and their dark partners can annihilate each other when they collide, releasing energy in the form of other particles, such as dark photons or other dark sector particles. Symmetric dark matter model could help explain the observed dark matter density due to the abundance of ordinary matter particles. Asymmetric dark matter proposes that the dark matter particles and their antiparticles or dark partners are produced with an initial asymmetry in the early universe, similar to the observed asymmetry between matter and antimatter in the visible sector. In the asymmetric dark matter model, the dark matter particles are assumed to be relatively heavy, with masses similar to the mass of the proton or heavier. The dark matter particles are also assumed to interact with each other through a new force carrier, such as a dark photon or a dark Higgs boson. Magnetic monopole dark matter is AL model that proposes that dark matter is composed of magnetic monopoles, which are particles that have only one magnetic pole, either north or south. In the context of dark matter, magnetic monopoles could contribute to the overall mass and gravitational effects observed in galaxies and galaxy clusters. They are proposed as a possible explanation for why there are no isolated magnetic charges in the universe. Mirror dark matter is a hypothetical form of dark matter that arises from the idea of a mirror universe or mirror sector where there exists a parallel set of particles and forces that are similar to those in our own universe, but with some differences. Mirror dark matter proposes that the dark matter particles are counterparts of the known particles in our universe, but with opposite parity. This means that they do not interact with ordinary matter through the electromagnetic, strong, or weak nuclear forces. They would, however, interact through gravity, which is why we can observe their effects on the motion of galaxies and galaxy clusters. Light dark matter is a type of dark matter that has a mass of less than 1 giga-electron-volts. Superheavy dark matter is a type of dark matter that has a mass of more than zeta electron volts. WIM-Scylla particles are ultra-heavy dark matter candidates, and they are also often referred to as superheavy or macroscopic dark matter. A WIM-Scylla particle would have a mass of at least 10 zeta electron volts, which is many orders of magnitude greater than the mass of typical WIMP candidates, which are often in the range of 10 to 1000 gigaelectron volts. These particles come from cosmological models involving cosmic inflation. In these models, it's possible for very heavy, stable particles to be produced in the early universe. Vector dark matter is a theoretical class of dark matter models that propose the existence of a new type of vector boson that acts as the dark matter particle. In particle physics, a vector boson is a type of particle that carries a force and has a certain kind of spin property such as a photon. Dark fluid is a concept in cosmology that unifies two phenomena, dark matter and dark energy. The idea behind this concept is that there might exist a single substance, or fluid, that behaves like dark matter in some situations and dark energy in others. Instead of these being two separate entities, they could be two different manifestations of the same thing. This hypothetical fluid would be influenced by scale, acting like dark matter at small scales, for example, within galaxies, and dark energy at large scales like between galaxies. Thank you for watching.